Every challenge question, chapter 8. I think this is the parametrics chapter. It is good. And now this question is very funny if you have learnt T formulas, and if you haven't, it's just not that hard anyway. You square both these two things, obviously, to get this and this. 2t all squared is 4t squared. I haven't bothered to square the denominators out. The numerator I can actually square now, and then I can put these together and just put them under the same denominator because they've got the same denominator. And now this and this come together to make plus 2t squared. And then this actually factorizes to 1 plus t squared all squared, which is nice because that all cancels to make 0. Hence, this is a circle, radius 1, center 0, 0. If you just Google T formulas and watch a video about them, and this will become clear as to why that was otherwise quite easy. This question I think I made a complete meal of. I'm not really sure, to be honest. I just tried to make some of this stuff. So why, I mean, this, firstly, you can use compound angles to get this. Cos pi over 6 is root 3 over 2, sin pi over 6 is a half. I then doubled it, I think. I wrote it again pointlessly, then I doubled it. Cool. And by doubling it, now I can square both sides, and I'll get 4y squared here, and then I can expand some brackets out. Imagine when you square this, it's this brackets times itself, so this times this is 3 sine squared, and then plus a cos squared at the end, and then 2 cos terms. Because that's cool, I'm going to use this identity to help me a little bit with this one. Firstly, 2x, which I'm going to put in here, is just cos 2t. And then I'm also going to say cos 2t, which is 2x, is also equal to 2 cos t minus 1. And now what I'm going to do is I'm going to put this 2x into here, but I'm going to use this one, I think, to go into there. No, I'm not. I think it's the other way around. I'm going to put this one into there, and this one squared will go into here. And it just happens when you do that, so just square both sides here and then times everything by 3. It just happens when you do that, when you put in 4y squared, which is all this stuff, into here, minus 2, which is this one, plus 2x, which I'm using this version of in here, and then plus 12x squared, which is this guy here, and then minus 3. It just happens that a lot of this cancels, right? Because you get 3 cos squareds here, but 3 sine squared plus 3 cos squared is just 3. And then the 3 minus the 2 minus the 1 just makes all of that go away, except for this term here. So all of this becomes just this thing squared plus this. Now this thing squared, of course, is, I think I'm actually not going to bother. I'm just going to move, I'm going to say root 3 squared is 3, and just take that out. Because now, of course, 2 sine t cos t is sine 2t by some other identity. And now, of course, this is sine squared of 2t plus cos squared of 2t all times by 3, which is just 3. And 3 minus 3 is 0, which is what they want you to get. There are probably easier ways to arrive there. This question is very confusing because I don't really know how the book has taught you how to do this question yet. So I can do this question with some effort, but what I'm saying is I think it's the first challenge question we've come across in this entire series that I'm not sure. So all the book has taught you how to do to sketch these graphs is do a massive table of t values and find a load of xy values and then draw it. I guess that's possible here. It's awful, but I guess it's possible. I'm instead going to do a couple of things that are more intelligent. So let's get out of sketch. Firstly, I just noticed that y is equal to x times another t. So we have this sort of weird line thing going on with the parameter t here. And when t is minus 1, we're not allowed, there's an asymptote there. But when t is minus 1, that's just y equals minus x. So y equals minus x is the asymptote, and we have some kind of asymptote going across like this. Other things you can just notice without doing anything majorly intelligent is that when t is 0, x and y are 0, so this goes through the origin when t is 0. It also, when t is plus or minus infinity, because these two things outweigh the top two things, you also get x and y as 0. So it's one of those equations that loops around. And when t is 0, you're here, but also when t is infinity, you're here, and when t is negative infinity. So it must be looping somehow and getting back to like a figure of 8 or something like that, and getting back to here eventually. So yeah, that's interesting. You can also find various other points where t is 1 is an obvious one to check, and you get 9 over 2, 9 over 2, which is somewhere over here. And like when t is 2, you get another nice point. But then you start getting bored of just finding points and start looking for a better thing. And the better way of doing it is using this equation. Basically, what this here says is that every point on this parametric curve lies on some line y equals tx for different values of t, and so therefore different gradiented lines. Let me just show you what that looks like, maybe if I get out Desmos. So we've got a line y equals tx, and here's the coordinate point of the thing that we're looking at. So basically, our point, whenever we have a point to do with this parametric curve here, it must lie on the relevant line y equals tx, which looks like this. So basically, when you have like t is 0, you're at 0, 0, we discussed that. And when you increase it, you must be on this very gentle gradiented line here. And you move slightly away from this because when you put t as 0.1 here, you end up with some values as your x and y coordinates. And you move away, but you almost must follow, like the position must always be on each of these lines. And these lines get steeper and steeper and steeper and steeper. And eventually, as we were saying, when t becomes big, the denominators outweigh the numerators, and you start crashing back down to 0, 0. So this is the idea, I think, when t is bigger than 0, is you gradually move away from the x-axis, always following these lines that are increasing a gradient, and then you move back towards it. So we make a sort of a loop going away and coming back. That's what the curve is going to look like. And then you can think about what happens when the line is negative, right? You still have to exist on this negative gradient. You still have to exist on each of these lines as you move away. And of course, you move away very quickly. And when t is -1, you don't exist at all because the denominator is negative. So then currently the parametric curve doesn't exist anywhere. But then when you move past it, you come back again from this area down here. And if I just delete this, I'll end up with the full curve here, which looks like what I was kind of trying to display as we move around. And this is what it looks like. Obviously, if you don't want to use the assistance of that kind of idea, I'll try and get rid of this. How do I get rid of this? That's really annoying. Let's get rid of that start bar. That's really annoying. I think if I press this and then, okay, good. So yeah, the other thing you could do, if you don't want to use that kind of idea, is to use a chapter. I think it's the next chapter after this one. No, it's not. Yeah, it's in the next chapter after this, in the differentiation chapter. You learn about parametric equation differentiation, which it gives to you like this. Now, the only thing that's interesting about this is this implies that when dy by dt is 0, dy by dx is 0, which is cool because dy by dx is 0 gives us horizontal stationary points. So to check for horizontal stationary points in a parametric setup, we can just check dy by dt equals 0. And likewise, because of this denominator here, dy by dx is plus or minus infinity when dx by dt is 0. In other words, the curve is, or the parametric curve, is just going straight up or down rather than straight across like horizontal stations. I'll call them vertical asymptotes maybe, even though we do sort of get there, so maybe that wasn't the right word. But you know what I mean. It's for this setup, the curve is straight across, and for this setup, the curve is going straight down. So let's do each of these. Let's do dy by dt equals 0. So dy by dt, I'm going to use a bit of quotient rule, even though I hate it. It's just easier when you're about to solve for 0 because you can just look at the numerator and ignore the denominator. So yeah, let's do that. T is 0 is a solution we can see, and therefore this graph is flat at t is 0, which corroborates with what the computer was giving us. So that's cool. Further to that, we can then solve t as the cube root of 2. If you put the cube root of 2 into here, you'll end up with 2 points that are slightly further back than 4.5 and slightly further up than 4.5. And so it ends up being roughly there, and you end up with a flat point there. Then you do the same for dx by dt. So you differentiate it, again, using quotient rule probably, just because it's easier. You set the numerator to be 0. You notice that there are solutions at t is the cube root of a half. And then when you put that into there, you end up with something slightly beyond 4.5 as your x coordinate and something slightly lower than it for the y. And that's a vertical point where the graph is parallel to the y-axis. But also, if you look here, you can also make dx by dt 0 by just making t massive. Because, oh, sorry, I've got both these wrong. This should be 1 plus t cubed all squared. Apologies. Of course, it's v squared on the bottom. I don't use quotient rule very much, so that didn't occur to me. But this is 1 plus t cubed all squared on the bottom, which means you have a t to the 6th term, and that outweighs anything on the numerator. So when t is plus or minus infinity, or when it goes there, dx by dt is also 0. And we already know when t is plus or minus infinity, we're at the point 0, 0, because again, these denominators outweigh the numerators. So we're back at the origin, and we also have vertical asymptotes there. And this corroborates with everything that the computer was saying. We start here, we move away, vertical asymptote here, horizontal asymptote here, and we head back to a vertical asymptote here when t is infinity. And then when t goes back from 0 and becomes negative, you head off this way because of this horizontal asymptote at 0. You must be heading off this way. You go off the asymptote, and then you come back through it and have a vertical at t is minus infinity up here. And that'll be your entire sketch. Cool, so that question was weird. This question here, now, when you're looking for the intersection of parametric equations, generally speaking, you can't just set this equal to this and this equal to this. And it doesn't work because, as we saw from this one, you've got different t values as you move around the curve. And so when you, I don't know where the other one's gone. Okay, so maybe this was like at t equals 2. And sorry, this is like at t equals 2. This is t is half. This may be over here where this intersection is. I'm making up maybe for the black one is t equals 3. But for this other parametric graph that's doing this, maybe t equals 5 here or something else that's random. And that means that, this is equivalent to, if we've all walked down the same corridor, so me and the people I've taught have all walked down the same corridor before, but we've never like actually collided with each other because we're doing it at different times, right? So you can't just set these x equations bits equal to each other because they might be here at different times. Like they'll be in the same place, but the t value is different for them to get there. Like maybe t equals 3 for the black and t equals 5 for the red. And so you can't just set these things equal to each other. So what you need to do is find the Cartesian coordinates or Cartesian equation, and then you can just set them equal to each other. So let's do that. So rearrange this for y equals t minus 1 over 2. And rearrange, I think I actually then just put that into there, right? Because 2t is y minus 1, so it ends up being quite easy. I decided to go the other way around for this one because I didn't want a square root. So I just said t equals log x, which means y is 1 plus log x all squared. And then you can just put x is e to the y minus 1 into here, and it clears out immediately. It's really nice. Expand it all out, solve it, you get y is minus 1, y is 2. And so when y is 1, x is equal to e to the 0, which is also 1. And when y is 2, you get x is equal to the 1, which is just e. And you end up with these two intersections. Now, this is different for the last question of the chapter, which is talking about particles that are moving and they collide. Now, if they're colliding, going back to that corridor example, that means that they are in the same place, but also at the same time. So when you're actually doing like a modeling question like this, you can just set these two things equal to each other because the x coordinates have to be equal and the times also have to be equal to each other for that collision to happen. Otherwise, they're just passing through each other, passing through different places, the same place at different times, which isn't collision, right? So, okay, we can just set these equal to, you times by t, you solve, you get t as a half or t is 2. Now, t as a half is, I think, justifiably must be the correct thing here, because if they collide when t is a half, that means that they won't be following these motions anymore because they've collided, and so t equals 2 is irrelevant. But the other thing you can do is you could put t equal to into the y coordinates, which remember also have to match. And when you put t as 2 into these, you end up with k as 0, which tells you can't have somewhere there. So therefore t as a half is the correct one to do. So again, let's put t as a half into these y's to make sure they match, and you solve and get k as 3 over 2. And then the coordinates of collision, well, you just put k as 3 over 2 into, well, actually, you don't even need it, right? Because you can just say t as a half is the correct one. 2 over a half is 4, and 3 times half is 1.5 plus 2 is 2.5 or 5 over 2, and that's the coordinate of collision.